Hello and welcome to my YouTube channel called Training Made Clear. Today we're going to be doing a lesson on basic electricity, part 2B. Before we continue with the lesson, I just wanted to help you find all my other training videos. So when you go to YouTube, type in the Training Made Clear into the YouTube search bar. For my fun channel, type in Percy's Discoveries. In the first video on basic electricity, part 1, these are the different subjects that we covered. So if you haven't seen this video, please make sure you've seen the video on part 1 before doing part number 2. Part 2, the effects in electricity, power and generation. We've done part 2A, and today's lesson will be on part 2B from magnetic fields onwards. In the previous videos, we discussed this picture of the river of electricity. It's a very nice picture which can help you understand the basic workings of electricity, like voltage is pressure, and current is flow, and resistance is ohms. So if you think of electricity like a river, this drawing can really help you a lot. Okay, point number 14, magnetic fields. A magnetic field is produced around any moving electric charge, positive or negative, whether in a conductor or free space. The magnetic field produced by a moving electrical charge is produced by a warping of the charge's electric field. This is caused by its relative motion. If the direction of the current is reversed, the magnetic field is reversed. All magnetism arises from moving electric charge. If a current flows in a helical coil like a solenoid, the magnetic field will be directed through the solenoid and out one end. The field curves around and re-enters the other end of the solenoid. This is similar in shape to the magnetic field produced by a bar magnet. Figure 27. Whenever an electric current flows through a conductor, a magnetic field is formed around the conductor. Figure 28. Left-hand rule of polarity. Moving electric charges are surrounded by a magnetic field, and magnetic fields interact with magnets. Point 15, measurement. Instruments designed to detect and measure electric current in circuits make use of the deflecting force on charges moving through the magnetic fields. The galvanometer and ammeter detect and measure electric current as it flows in a coil pivoted between two poles of a permanent magnet. As the current in the coil increases, the moving charges are increasingly deflected by the magnetic field. By standardizing the scale, the quantity of current in amperes can be determined. In measuring current, the ammeter is connected in series in the circuit. A voltmeter is used to measure the potential difference or voltage drop between points in a circuit. Like the ammeter, it has a movable coil positioned in a magnetic field, but the voltmeter has an extremely high internal resistance. The trickle of current through the voltmeter depends on the potential difference between the terminals of the meter. The voltmeter is connected in parallel across a resistor to measure the potential difference in volts. Point 16, types of power. There are two types of electrical power used in the oil and gas industry: direct current DC, alternating current AC. Direct current is a direct, continuous supply of power where the electron flow is always in the same direction. A simple example of a DC circuit is a battery powering a flashlight. DC power is used in the industry for a wide variety of purposes, including electronic control, instrumentation, communications, variable speed motors, computers, fire and gas detection systems, corrosion prevention systems, electrostatic precipitators, AC generation excitation, inverter supply, emergency lighting, and arc welding. Alternating current, commonly known as AC, is an electrical power supply where the electron flow is reversed at regular intervals. The voltage and current builds up from zero to maximum in one direction, returns to zero, and then builds up to maximum in the opposite direction. This cycling is continuous as long as there is a current flowing. In the SI units, the frequency of these sine waves of alternating currents is measured in hertz, with 1 hertz equal to 1 cycle per second. AC power is extensively used in the industry for the purposes of motor drives for pumps, fans, compressors, machinery, etc., heating, lighting, air conditioning, DC power via the transformer or rectifier. Nearly all electric motors used within the industry are three-phase AC motors. Point 17, power generation. There are many ways that electricity can be produced. Direct current can be produced by pressure. A quartz crystal pressed between two metal plates will produce an electric force that is variable in proportion to the pressure exerted. If two dissimilar metals are joined together at one end and the junction is heated, their voltage and current will be proportional to the amount of heat applied. This system is called a thermocouple. Figure 26, and is used for temperature measurement. When light falls on materials such as cesium or silicon, electricity is produced. Solar cells made from silicon will convert sunlight directly into electricity. Electricity can also be produced from chemical cells, and it is a common source of power. These cells can be divided into primary cells and secondary cells, storage batteries. Point 17.1. Primary cells produce electricity by expending chemical energy in a reaction between conductors of different materials or substances through an electrolyte. The electrolyte can be either a liquid or a paste, but it must always be moist. When the different metals or substances are connected by a conductor, providing a complete circuit for electrons to flow, a voltage is produced. The most common type of dry cell is made up of a zinc casing filled with ammonium chloride, cell ammoniac paste, with a carbon rod inserted in the center. When a complete circuit is made, zinc ions flow through the electrolyte to the carbon rod. Eventually, the zinc casing will oxidize or corrode, and no more power will be produced. And there you can see the diagram for the cell. 17.2, secondary cells. Storage batteries are made up of a number of single storage cells. A common example is the car battery, which is a lead acid type. Each cell produces 2 volts. If 6 cells are connected in series, a 12-volt battery is obtained. Batteries are used in UPS systems. The construction of a lead battery is quite simple. 2 lead plates are contained in a cell filled with dilute sulfuric acid. In a fully charged battery, the plates are lead peroxide, PbO2, and the negative plates are pure lead. As a result of the reaction between the 2 plates through the electrolyte, the battery discharges. The 2 plates absorb acid from the electrolyte and become lead sulfate. To reactivate the battery, it is necessary to recharge it again with a direct current that will reverse the chemical reaction and return the acid to the electrolyte. Now there you can see a table in front of you, and it's no good if I don't explain this table to you, so here goes. There is the table, and I'm going to go through the explanation. This chart is showing the chemical reaction inside of a lead-acid battery, such as a car battery, during discharge, and then the reverse reaction during charging recharge. When the battery is discharging, the top equation represents Pb plus PbO2 plus 2H2SO4 to Pb to SO4 plus 2H2O. That is the top equation. Where Pb is the lead negative plate, PbO2 is the lead dioxide peroxide positive plate, H2SO4 the sulfuric acid electrolyte, PbSO4 the lead sulfate, H2O is water. What happens? Both battery plates react with the sulfuric acid. Lead sulfate forms on both plates. Water is produced. Electrical energy is delivered to the load. The result? Acid concentration decreases. Water content increases. Battery voltage drops. This is why a discharged battery has lower specific gravity or weaker acid. Here's the formula again. This chart is showing the chemical reaction inside a lead-acid battery, such as a car battery, during discharge, and then reverse reaction during charging or recharge. When the battery is charging or recharged, the lower equation is simply the reverse. 2PbSO4 plus 2H2O becomes Pb plus PbO2 plus 2H2SO4. The charger forces current back into the battery. What happens? Negative plates. Lead sulfate PbSO4 is converted back into lead Pb. Positive plates. Lead sulfate PbSO4 is converted back into lead dioxide PbO2. Electrolyte water is converted back into sulfuric acid H2SO4. The result, acid concentration increases, specific gravity rises, battery voltage rises, energy is restored chemically. Why specific gravity increases during charging? During discharge, sulfuric acid becomes consumed. Water is produced. During charging, water is consumed. Sulfuric acid is produced. Therefore, the electrolyte becomes stronger again. A typically fully charged battery has a specific gravity around 1.265 to 1.280, depending on the manufacturer. A discharged battery may be 1.120 to 1.180. What happens near full charge? Once most of the lead sulfate has been converted back, the battery voltage rises sharply. Charging current decreases for smart chargers. Water begins splitting into hydrogen and oxygen gas. This is the gassing stage. 2H2O becomes 2H2 plus O2. This is why flooded lead-acid batteries can lose water and occasionally need topping up with distilled water. In simple terms, think of a lead-acid battery as storing energy by moving sulfate ions. Discharging, acid gets weaker, lead sulfate builds up on the plates, battery supplies power. Charging, lead sulfate is removed from the plates, acid gets stronger again. Battery stores power. The chart is showing that the charging reverses the chemical changes that occurred during discharge, restoring the plates and the sulfuric acid to their original state. Another popular type of storage battery is the nickel-cadmium, where the positive plate is nickel hydroxide, the electrolyte is potassium hydroxide, and the negative plate is cadmium hydroxide. The voltage produced in these cells is 1.25 volts. There's a diagram of a whole lot of different types of nickel-cadmium batteries. Storage batteries do not actually store electricity, but do store chemical energy that can be instantly converted into electrical energy. In industry, secondary cells in the form of storage batteries are used to provide backup and emergency power in the event of power failures. These systems provide lighting and power to critical operations such as pre-post lubricating and seal oil for compressors and electronic instrumentation, especially control panels. These storage batteries are normally connected together in series to provide the necessary voltage and are provided with an automatic recharging system to ensure the batteries are fully charged for use in case of emergency UPS. Mechanical devices. A motor changes electrical energy into mechanical energy, while a generator produces electrical energy from mechanical energy. The electric motor demonstrates a common application of the interaction between moving charge and a magnetic field. In a motor, electrical energy is converted into energy of motion. A simple motor can be represented as a loop of wire attached to a source of direct current. The loop is pivoted to rotate in a magnetic field. As electric charge moves along the loop, deflecting forces begin to cause the loop to rotate. To keep the loop rotating, the direction of the current in the loop must be reversed every 180 degrees. A device called a split ring commutator is used for this purpose. In 1831, Faraday showed that a moving magnet through a coil of wire would generate a current in the wire. If the magnet was plunged into the coil, current flowed one way. When the magnet was removed, the current direction was reversed. This phenomenon is called electromagnetic induction, and it is the principle underlying the operation of a generator. As long as the magnet and coil move relative to each other, a potential difference is produced across the coil, and current flows in the coil. A potential difference is also produced if the magnetic field through the coil grows stronger or weaker. The greater the change of magnetic flux through the coil changes, the greater the potential difference produced. Lenz's law states that the direction of an induced voltage tends to oppose its cause. Lenz's law applies to motors, where a current carrying wire moves in a magnetic field. That movement in turn causes a current in the wire that opposes the original direction of the current in the wire. Because electric current cannot occur without a potential difference, this opposite effect is sometimes called back EMF. Large current flows when a motor is started. As the motor begins to turn rapidly, a large back EMF is induced and the net current in the motor drops. If a large load is applied to the motor, slowing it drastically, the back EMF will drop, and the sudden rise in current amps may cause overheating and burn the motor out. Point 19. Transformers. In order to transport electricity over a long distance, transformers are used. These can be step-up or step-down transformers. Voltages are stepped up voltage increased at the producing station and stepped down at the user end. The reason for stepping up the currents are: the current passing through a conductor power cable loses energy due to the heat effect. The amount of loss is proportional to the number of amps or current and the size of the conductor. The larger the conductor, the less power loss. Electrical power is calculated by multiplying the voltage by the current in amps. For example, if 960 watts are required, it could be supplied by one of the following scenarios. You could have 120 volts times 8 amps equals 960 watts, or 60 volts times 16 amps is 960 watts, or 240 volts times 4 amps is 960 watts, or 960 volts times 1 amp equals 960 watts. The most efficient combination for transporting 960 watts would be 960 volts at 1 amp, which is 16 times more efficient than 60 volts at 16 amps. Watt W is the unit for power or energy transfer. When the power reaches the user, the voltage is stepped down to the required voltage of that user. Transformers work on the principle of induction. When a conductor that carries a current surrounded by a magnetic field moves across another conductor, a voltage is produced in the second conductor by induction. The magnetic field movement is caused by the alternating nature of the current. Because 50 Hz AC rises from 0 to peak and back to 0 100 times every second, the magnetic force surrounding the conductor moves in and out 100 times every second. If another conductor is placed so that the lines of force move back and forth across it, a current will be induced in the second conductor. The principles to remember for transformers are: the conductor carrying the generated current is the primary, and the conductor carrying the induced current is the secondary. The two conductors are insulated from each other. The induced current will have the same frequency as the primary current and will also be alternating current. This basic construction of a transformer consists of an iron core with the primary conductor coil windings on the one side and the secondary conductor coil windings on the other. Conductor coils are wound around the core to intensify or increase the strength of the magnetic field, and the iron core provides a magnetic path. A transformer does not generate power, but it transfers power from one coil to another by magnetic induction. Transformers are almost 100% efficient. A transformer is a device that transfers power from its primary circuit to its secondary circuit without any large loss. Transformers step up or step down voltages but do not alter the kVA of the primary circuit. kVA means kilovolt ampere. Manufacturers rate transformers and generators in kVA rather than in watts because the power factor of the equipment and system is unknown. Electricity is usually charged if being bought in kilowatt hours, as a kilowatt hour is a measure of energy and hour is a measure of time. Kilowatt hour is the measure of energy consumed in a given time. Any transformer that has more turns of the conductor windings in the secondary is called a step-up transformer, producing a voltage in ratio to the number of windings on the primary coil. If a transformer has 10 windings on the primary coil and 100 windings on the secondary coil, the ratio is 10 to 1. If the voltage of the primary is 200 volts, then the voltage of the secondary coil will be 100 divided by 10 times 200 equals 2000 volts. By the same principle, transformers that have fewer windings on the secondary coil are step-down transformers. So, if a transformer has 10 windings on the secondary coil and 100 turns on the primary, the ratio is 1 to 10. If a primary voltage is 100 volts, then the secondary voltage would be 10 volts, that is 10 divided by 100 times 100 equals 10. The ratio of the number of coils in the transformer is called the turn ratio. The turn ratio will decide the voltage output of the secondary coil relative to the primary voltage supply. The turn ratio is always given with the secondary number stated first. Auto transformers are used when the transformer ratio is 5 or less. Auto transformers do not have primary or secondary windings, but have one winding only. Part of the winding is used for both the primary and the secondary, while the rest of the winding acts as either a primary or a secondary, depending on whether it is being used as a step-up or step-down transformer. Auto transformers are less expensive to manufacture and are often used to reduce voltage applied to a large AC motor during the start period. They can be used in transmission systems to boost the voltage back to the transmission levels. Although transformers are almost 100% efficient, there are some losses that can occur. These can be divided into no load loss. That is when no current is being transmitted. These can be divided into two types. The first type is the eddy currents. Eddy current losses are circular induced currents that flow around the lines of force. Eddy currents are not desirable as they cause heating of the core. A method for reducing eddy currents is to construct the core from a number of thin plates with insulation material sandwiched between each plate. This system of construction is called lamination. The second type of no load loss is hysteresis loss. This is caused by magnetizing of the core, first in one direction and then in the opposite direction. Each time the polarity reverses, some energy is used to overcome the magnetism left behind. Load loss. This occurs in the windings when the current is flowing and is caused by the resistance in the copper windings. All losses result in heating of the transformer. Small transformers do not require any cooling as the temperature increase is quite small. The larger the transformer, the more of a problem heating effect becomes. Medium-sized transformers are installed in oil-filled casings, with the casing having fins that act as heat sink heat removal. The special high-resistance oil helps to electrically insulate the windings and transfer heat to the casing fins by thermal circulation. Large transformers have a fin fan mounted on the top or the side of the casings to assist in the cooling of the oil. Number 20. Direct current source. It is not economical or practical to transmit DC power over any large distance due to the fact that it cannot be transformed, no polar movement, and power losses are incurred. Direct current is nearly always supplied from an AC source. To convert AC to DC, a device called a rectifier is used. There are two types. One, rotary, which is basically a DC dynamo driven by an AC motor. Two, stationary, the most common type being the silicon rectifier or diode. This works in much the same way as a non-return valve. It allows current to pass in one direction only and prevents the reversal of direction of alternating currents, so allowing only half the AC cycle to pass. This results in a pulsating flow of current in one direction only, or in effect direct current. It is sometimes necessary to produce AC power from a DC power source like batteries during a power failure so that the essential equipment continues to operate for a period. This system is sometimes referred to as an unlimited power supply UPS. The AC power is produced by an inverter using the batteries as a source of power. Convert AC to DC using a silicon rectifier or diode. What you're going to be seeing here is a picture of basically a battery charger, how a battery charger works. The AC input sine wave passes through the step up or step down transformer. The positive side of the sine wave is shown in red and the negative side is shown in blue. In the positive AC sine wave, the current flows through the diode D1 and is blocked from flowing through D3 and D4 as it flows towards the load. In the negative AC sine wave, the current flows through diode 3 and is blocked from flowing through D1 and D2 as it flows towards the load. This would produce a resultant output wave form as shown by the dotted lines. Adding the capacitor would produce the wave shown in the black line, the waveform with a capacitor. This is the principle for a battery charger. So I hope you enjoyed watching this video. Thank you for watching. And if you like it, then please subscribe and share it. And stick around for the test to test your knowledge. Thank you for watching.